Okay, guys, so for this section on thermodynamics, I am going to go through some past exam problems. This one is from spring of 2019. So we're going to talk about thermal cycles. As I go through this, I'm going to do something a little bit unusual. I have Professor Spilio's lecture notes here, and as I go through, I'm going to pull equations from these lecture notes and show you exactly where from the lecture notes I am taking them. I will also put them in the folder. So it's just sort of a consolidated place to look for equations and also get some background on those specific equations as well. Your book is also a good place to start, but this is just sort of a condensed version with some specific examples of what we're going to be using right now. Okay, so in a thermodynamic cycle, we have a thermal cycle where uh, essentially we have a series of linked thermodynamic processes. So from A to B, that's a process, from B to C, that's a process, and from C to D, that's a process. Each of these processes often have their own labels. So we have, or they will have their own labels. So we have isothermic, isobaric, and isovolumetric. I just want to point out something very interesting here too. So isovolumetric, um, as we see, as we go from A to B, we notice that the volume doesn't change, right? So volume here is V naught, volume here is V naught, right? Because it's the same on the y-axis the entire time. From B to C, we have isobaric. So we notice that the pressure doesn't change here. At B, the pressure is P naught. At C, the pressure is P naught. The volume does change, but the pressure remains the same. Okay. Then from C to D, we have isovolumetric. Notice that we have 2 V naught here and 2 V naught here, but that the pressure does change from these two states, right? So we go from P naught to 3 P naught, so we change by 2 P naught right in the middle here. Or P naught, yeah, by 2 P naught in the middle. Okay, so what can we tell from these? So in this graph, we have a changing relationship between pressure and volume, right? As we go through different thermodynamic processes, right, within the cycle. Okay, so some backgrounds on thermal cycles. So a thermal cycle may be something like an engine. So it's a process, okay, that produces work in exchanges basically work and heat, and it's called a thermal cycle. Okay, so there's a closed path, right? We have a closed path here uh, in a PV diagram for a thermal cycle. Okay, and that closed path means that so we know that the change in energy, right, in a cycle is equal to the Q variable, and that Q variable is net heat transfer. Okay, so we have net heat transfer as Q, and then we have the work of the cycle as W. Okay, so our change in energy for the closed path, our net change is going to be 0, right? Because we're always going to return to that initial state, right? So we're coming and returning to our initial state as we're moving through that closed path. And so we can model Q of the cycle is equal to W of the cycle, okay? And so that means that we can use some general equations when we address these thermal cycles where we're relating work and heat as things change, okay? So let's go ahead and get started. Okay, so in our unknown thermodynamics cycle here, let's see what we can determine using the problem statement. Okay, so we have a thermodynamic cycle that is being used as a heat pump, okay, with a coefficient of performance of n equals 10. So our coefficient of performance basically tells us the heat supplied or removed by the system divided by the work required, okay? Um, and that coefficient of performance is just sort of a measure of how much we would need to supply based off of and the work to get what we want, okay? We're also told that the heat pump uses a diatomic gas. On page 18, there are two different coefficients for this D variable that we're going to use in our equations. So if we have a monoatomic gas, we're going to use this D equals 3 constant. And if we have a diatomic, we're going to use this D equals 5 constant. So that is on page 18 for more background. Okay. So we know these three processes. So we're going to use the notes and get the equations from the notes to set up these three processes, but we don't know D to A. Okay. So we are trying to find this last piece, okay? So we're given a coefficient of performance, and we know that equation, and then because we have a cycle here, we can say that the net work, is going to be equal to all of the work done by each separate process, and we're going to add those together. So we want an equation where we can relate, we're going to be relating the coefficient of performance to the Q of the cycle. Okay, so let's go ahead and set that up. Okay, so in order to do this, what I'm going to do is I'm going to set up a graph of each, just like a little chart, and I'm going to find Q and W for each of the separate thermodynamic processes. Page that I'm trying to find here. Okay, so page 28, so that's where it starts. Okay, so we have an isovolumetric process. So this first one is actually, this is isobaric. Let's go ahead and take that one because we do need it as well. Okay, so what is Q for an isobaric process? Well, if we look right here, we have D over 2, d over 2 plus 1, right? And that is times P change in volume. Okay, so just a general equation. Okay, so what about isovolumetric? Because that's the other two that we have here, right? We have isovolumetric here and here. What is the general equation? Oh, sorry, also I'll do work. So work is also equal to P delta V. Okay, so isobaric and then isovolumetric. So we have that here. Okay, so what is Q? Q is right there. So it's going to be D over 2, right, times V delta P. Okay, so D over 2 times, sorry, 2 V delta P. Okay, and then our work is equal to 0, right? And that should make sense because the equation for work, so we notice that we have an integral for work times P delta V, and that's equal to 0. Because we're looking at the change in volume that doesn't change when we have an isovolumetric system, right? So if we're integrating over the change in volume and the volume is the same, we're going to get 0. Okay? All right, and so for D to A, what is that? We actually don't know for this system, right? So let me label these. So we're trying to find, this would be, so this is QAB, QBC, QCD, and then this would be QDA, so coming back around. Okay, our sign convention is also important here, and here's how we're going to model it. So A to B, that's going down, right? That process is going down, so this is a negative sign convention. So QAB is going to be negative. QDA, let's see here, QDA is also going down, right? We have a negative change for QDA, so that is also going to be negative QDA, okay, in our system. And additionally, this work is also going to be a negative, okay? All right, so now we set up our general equations. So what even are these values? Let's plug in what we have and then try to get some actual equations here, right? Okay, so how are we going to use these? Why do we care, etc.? Oops, sorry. All right. So our general idea, what we're going to do is we're going to find this QH value. So this is the heat supplied or removed, or heat supplied to the system because we have a heat pump. It would be heat removed if we had a cooling process. So this would be heat removed if it was a cooling process, but we have QH. This H subscript means heat supplied. Okay, so our heat supplied terms so this is the heat going into our heat sink. So A to B and D to A are going to be our heat supplied. So we're putting it in. So it's our heat supplied. So as a starter here, we're going to say that we know that our QH is equal to, just by looking at the graph, we have negative QAB minus QDA, right? And this QH is just kind of the absolute value of those guys, right? So it's just going to be QAB plus QDA. Okay. So we can put them in as negative. Either way, I don't think it'll really matter. Their sign convention will be the same. Okay, so we have QH. Now we want to find this W for this bottom term because we have COP, we're given n equals 10 for a COP. And then we want to basically set up this equation for COP because we can just say, so what we're going to end up with, right? We're given a coefficient of performance. We're going to say 10 is equal to this QH over W. So let's find QH. We know that that's QAB plus QDA. and then divided by W, that's just going to be all of these terms added together. Okay, so we want to just find all of our heat transfer values so that we can use our equation. Okay, so what are our heat transfer values that we can plug in? So, and then W would be QAB, but I apologize. Okay, so let's find them all. What do we have? What do we need? Okay, so we're going to find them from looking at the graph, and then I'm actually going to make both of these a little bit smaller, and then we're going to just kind of like zoom in and out so that we can see the graph. Okay, I apologize if this is like hard to see on your screen. I know I have a lot of things going on here. Now that we found our terms from here, I'm going to go ahead and take this off the screen. Okay, because we got what we needed for our general equation. I showed you where they came from. Okay, and I'll leave the page numbers in here. Okay, okay, cool. All right, so what about this first one from A to B? Okay, so from A to B, what is the volume? Well, from A to B, the volume is, so we're going to have, we also have, okay, so we're told that we have a diatomic gas, so D is going to be 5 for this whole problem, right? So we're going to plug in 5 over 2, and then our volume from B to A, so our volume from, or sorry, from A to B, so our volume is V naught, it doesn't change, right? 5 over 2 V naught, and then what is our change in pressure, okay? As we go from A to B, our pressure changes from 2 to 2 P naught to P naught, so our pressure change delta P is going to be equal to P naught. Cool. All right, so then for this one, what do we have for the isobaric process? That one is going from B to C for isobaric, right? B to C. So we have 5 over 2, just plugging that in, right, plus 1. And then what is our change in pressure for isobaric? Okay, so isobaric, we have the same pressure, right? We're going from B to C, so it's going to be P naught that whole time. So let's go ahead and put that in, P naught. What about the change in volume from B to C? Well, we start at V naught, we go to 2 V naught, so it's just going to be V naught is our delta V here. P naught, V naught. Okay, cool. All right, now for this one. So 5, plugging it in for D, so 5 over 2 because we have a diatomic gas, so it's just the constant that we're using. Then we know that we have V naught, right? Or what? Maybe we don't actually. Sorry. At from C to D, what's going on here? Oh no, we don't, right? So what is our volume? We have 2 V naught at C and D, so this is our volume the whole time. So we're plugging. So for our volume term, we're plugging in 2 V naught because that's what the volume is at that point, right? We're just looking at the graph using the values. And then we need our change in pressure, Okay, so 2 V naught, so from C to D. What is our change in pressure? We go from P naught to 3 P naught, so our change is going to be 2 P naught, right? Okay, so we're going to have 2 P naught. Okay, cool. All right, things down here. So for AB, what did we have? We had -5 halves V naught P naught. For BC, we should end up with, I'm just looking at the final table here to make sure that we have -5 halves. Then we have 7 halves, right? Because it'll be 5 halves, right? Plus 2 halves. One is going to be 2 halves. So 7 halves, P naught, V naught. And then QCD is going to be 4, right? Or 2 times 5 over 10, right? Times 2 again. So 4 times 5 over 2, 20 over 2. So that's correct. So 10 P naught, V naught, right? You can work that one out for yourself. And then we have negative QDA for that one. 0 P naught, V naught, 0 negative WDA. Okay, cool. All right. So what we're going to do, we want to find the coefficient of performance. So we're looking at the cycle. For the coefficient of performance, we're taking the work from the W cycle, which is going to be equal to the heat supplied, or sorry, with the sum of all of the heat, and then QH is the heat supplied to the hot sink. Okay, so we're actually looking at this. We don't actually use this work piece here. They just had it in your solution, and I wanted to explain where the numbers came from, but it ends up not really being relevant for our particular problem. Okay. Okay, so what we're going to do now that we have everything, we're going to use this, right? So the coefficient performance is equal to 10 is equal to this N equals 10, which is equal to QH, which is that the H value is the heat supplied. So we took the negative ones, right? The ones that were going down, with the arrows going down where they were being supplied, okay? And then we're dividing it by the net work. So we have QAB plus QBC plus QCD plus QDA. So let's like just put all those in. So I kind of skipped ahead and worked out the algebra because I didn't want this video to be like years long because it's already getting pretty long. Um, so, um, okay, so just to recap. So I know that my equation for this, for COP, is the absolute value of the heat supplied divided by the work required. So on the top, I believe that I might have misspoken when I introduced this, so I just want to point that out. Okay, so QH is the absolute value of those guys. So we're dividing it by the work. So the work is not we're not taking the absolute value of that one. So just want to correct myself there. Okay, so when we're plugging this in on the top, we're going to need the absolute value of this guy and then divide it by the work. So all we did here, so this was our equation, right, that we started out with. And then we plugged in all of the terms, okay, that we found. And we talked about those over here. So we plugged in like QAB, BC, CD, DA, etc. Okay, and we modeled the ones that were going down, right? One going down is a negative heat transfer, okay? So we plug them in, all right, and we know that this COP is equal to 10, so we have 10 on one side of the equation. So what I did was I multiplied both sides by the denominator, so now I have this 10 multiplied by the denominator that was moved over here is equal to the numerator, okay? And then because I have this P naught V naught term, I grouped all of the coefficients of this one. So I have negative 5 halves plus 7 halves plus 10 times P naught V naught. So I have 2 over 2 plus 10 P naught V naught. Okay, so 11 P naught V naught, right? Minus this QDA. Sorry, let me just make sure I keep my parentheses in the right place here. Okay, and then I have this equal to the top part. Okay. Feel free to pause if something that I'm doing doesn't make sense, or if you catch a negative, leave it in the comments. If I made some small error here, let me know. Okay, so then I have this guy. Okay, so I grouped this, and I have 11 P naught V naught minus QDA. So then I have, I'm going to take this 10, negative 10 QDA, and I'm going to move it over to the sides of QDA here, and then I'm going to add 10, so I have 11 QDA, and then I subtracted this piece. So I grouped all of my P naught V naught terms, and then I grouped my QDA term, because this is what I'm trying to solve for. Okay, I'm trying to solve for QDA in terms of P naught V naught, right? Okay, so then I have 110 minus 5 halves, so I turn that to 220 over 2 minus 5, right? So I have 215 over 2, P naught V naught is equal to 11 QDA, and then I'm going to divide by 11, and I'm going to get 215 over 2 P naught V naught is going to give me this absolute value of QDA, okay? Remember that my QDA is negative, right? Because I have a negative heat transfer, right? Because this is going down. So in the end, I would just need to be careful with my sign convention here. Okay, just because when we did solve this, we were taking the absolute value to find this 10. So when I'm doing this, I'm solving for this QDA, but I just want to be careful about the sign convention here. Okay, so just make sure to be cautious about that. Okay, so I'll go ahead and stop this problem, but I just quick recap. So we have a thermodynamic cycle, right? So this whole thing is a cycle, moving around that cycle. It's composed of thermal processes, okay? The equations for the thermal processes we can look up, or we can kind of derive ourselves using the work integral. Please refer to Spelio's lecture notes that I kind of brought up throughout the course of this example problem. Okay, so we have all of the processes, right? We had one unknown process, but we were given a coefficient of performance. So we used the equation for the coefficient of performance for a heat pump, right, where we had heat supplied, right, the heat supplied, and it was supplied by D to A and A to B. So we put that on the top, and then we looked at the work required. And the work required was just the total heat transfer of the cycle, right, all of the pieces. So all of the pieces. So we, on the top, we had the dA term in the heat supplied term, And we also had it in the bottom on the work required term, okay? And because we knew this COP, we just did algebra to solve for QDA, okay? In order to find all of our equations for this QBC, for AB, BC, and CD, the known processes, we looked up our known equations for these known types of processes on page 28 in the lecture notes, okay? More background was there as well. We used this D equals 5 for a diatomic gas constant, okay? And we plugged that in. And then we looked at each of these individually from A to B, right? From A to B, we saw the change in pressure was P naught, the volume stayed the same, so we plugged in the volume and pressure values. We did that for the same thing for each of the separate processes, where we plugged in our knowns and we found the terms that we needed. We also did this for work, but this was a little unnecessary for this problem, but good to know. Okay, and then we just used some algebra to solve for our QDA.